dear friends, I've got the pleasure to show you some amazing things about water on the frame of chemistry. You mustn't be scared about such a big names and formulas and all of these things that we dreaded in school. It is very interesting actually, and I pledged and I promise that I'm going to explain every single thing. It's going to be very interesting because we're going to learn many things about water and the wonders of water. It is actually an amazing substance. If you think about it, it's just a plain thing. Water, it's all around. It's raining from the sky. It's running from the tap. It's all around. But you'll be surprised how many things about water you didn't know that they exist and that they can explain its unusual properties. First, I would like to say, if you look for sensational videos where you can watch lying in a Sunday afternoon just to entertain you, half sleeping, this is not for you. But if you look for a knowledge that's going to enhance your life and make you more knowledgeable, more wise, more practically gained some skills, this is for you. But obviously I would like to have your attention. With half attention, please don't even start. You're going to do totally injustice to yourself. I spent 7 days just to prepare, full 7 days just to prepare the lectures, and another few days more to record it. So it's not going to do only injustice to you if you're going to just casually watch it, but it's going to do injustice to me. And I'm giving you this all information for free. I studied for many years, and I believe if you would like to increase your knowledge, your intellect, your abilities, it will be great. I set this video for you, but I would like first your attention and second your commitment. So that means if you start the lectures, if you don't understand something, please go back and start until you get it. As I said, I'll try to make everything possible so understandable, so that you cannot have difficulties understanding it. Only one difficulty that you're gonna have is my accent, but unfortunately I can't change that. And if you look at it, and the flip side, it's actually it's not an impediment. It's actually an asset, because you're going to pay more attention to, you're going to listen more carefully what this guy with the funny accent is going to say. So that's going to be great for you as well. In this lecture, we're going to learn many interesting things. How can, for example, solid iron, not hollow iron, like some shape like a ball, you can put it in water, obviously it's going to float. But if you put solid iron on the water, it's going to float. We're going to learn how you're going to do this. Why the water is liquid at room temperature? How can water rise up? That's not a geyser, eh? That's not a geyser. Without a pump, without any human interference, can rise up 130 meters. That's not a geyser, I'm going to say. It's not a waterfall, it's nothing like this. It's amazing how actually water is washing everything, hands and many other things. It's actually watching how the microwave that we've got it in our house, how the microwave actually heats the food, but doesn't heat the dish that it is inside. Say if you put a normal dish with the food in the ordinary oven, is going to heat both, but the microwave doesn't do it. How the things rust and how can we protect them from rusting? Is seawater good for drinking? That means if you have to survive, can you drink seawater? On the other hand, is normal water poisonous? Can you poison yourself with normal, plain, cleanest water? Can you do that? Is that possible? and many other things. For the people that like cooking, I love cooking. I'd like to say, how can you cook the most delicious beans without boiling them? Actually, that's going to be very interesting. And I promise you, with the secrets that you're going to learn in this lecture, very practical secrets, you're going to learn also how to save a lot of on your electricity bill by doing some very simple things from physics and from chemistry that going to make your cooking first much faster, and that's going to save your electricity bill. So it's going to be a science, but it's going to be fun science, I promise you. And it's going to be explainable. I'm going to explain it. Every single thing I'm going to say, I'm going to explain it many times, and I'm going to repeat it. I just need your commitment, and if I say something that you don't understand, try to come back, make a connections, and things like this. Is not a Facebook scrolling up and down. I need your commitment. So that means spend time with it, and I'm promising you, you're not going to regret it. Your knowledge is going to be increased. I'd like to start with the beautiful quotation from Ellen G. White, which she wrote approximately 160 years ago, where she says, "The poet and the naturalist have many things to say about nature, but it is the Christian who enjoys the beauty of the earth with the highest appreciation, because he recognizes his Father's handiwork and receives and perceives his love in flower and shrub and tree. No one can fully appreciate the significance of hill and vale, river and sea, who does not look upon them as an expression of God's love to man." So that's one of the very profound quotations about how we look at the nature. The Bible also tells us, I just want to make another caveat. This is not going to be a theology lesson. I'm not going to indoctrinate you on anything. I'm just quoting a Bible because I believe it's an eternal book. And that's just the introduction. In Psalm 111 verse 2 it says, "The works of the Lord are great, and sought out of all of them that have pleasure therein." That means blessed are they that contemplate the works of the Lord. And Psalm 92 verse 4 it says, "For thou, Lord, hast made me glad through thy work. I will triumph in the works of thy hands." Some of the translation says, "I will sing over you make me sing over the work of your hands." Why is like this? That actually contemplating nature, contemplating the laws of nature, actually points us something much deeper, much more profound that we meet in our everyday life. It is very simple, simply because the laws, every single law, obviously shows to a lawmaker. You can't have a law without having a lawmaker. And therefore, the quotation where it starts, only the Christian can appreciate fully the nature and the laws of nature, simply because it sees the finger of God there. And I'd like to say it's, you take any book of chemistry, I'm talking about a good written university book of chemistry, physics, biology, and you're going to see clearly, actually you're going to see such a harmony, such a beautiful order, that you're going to see the hand of God. It's actually the same like reading the Bible. It's incredible. Such a harmony, such a perfection on everything. So it's my pleasure. I had to spend hours and days to prepare this lecture, to present it to you, and if I can transfer some of my excitement on the beauty and of the joy of science, which reveals God. Many people say, "Look, science denies God." That is absolute rubbish. True science reveals God, doesn't deny it. False science, yes, it can show many things like evolution, that the man came from the apes and things like this. That's not a science. That's a presumption. But the true science actually shows us the creator, because you can see clearly the laws that's related. Now you can say, why are you selecting water? Water is ubiquitous. It's all around. Look, if you give me a stone, if you give me a piece of iron, if you give me the air or whatever substance your eyes can stop on, I can make the same series of lectures all throughout, simply because everything in the nature is subject to the nature's creator and nature's creator's laws. And when you contemplate even a simple stone, you can see such a beauty in the science that goes into it. And you can, one single pebble, one single speck of sand, one single dust particle can show volumes of science. You won't believe it. One atom, it's so full of the care of the creator and his laws that is stupid not to get into that and delve into that and learn about that, because you're gonna see all throughout the beauty of all of this science, and it's incredible. We're not talking about here only the theoretical aspect. The theoretical aspect is fine and good, but it's going to help you with so many practical things. And this is why it's worth. It's not only mind development, showing you another perspective, but also is going to help you with many practical things, as I said to you just now. I'd like to say water, it's very important thing, and I'm saying a trivial thing now, but do you know that 1 million people die every year for lack of proper sanitation and any diseases that are connected to unsafe water? 1 million people. That's disaster. That's disaster. And it could have been helped, of these people could have been helped with the achievement of science that we enjoy, and if they could have known a little bit better how to make their environment a little bit more hygienic, and the water that they use, that they can purify it, and many other things. So this is why water is crucially important for us. But it is important. We not only just to know it, but also to practice what we have. Then we have a great benefit. In the beginning, I'd like to start with some questions, and you can answer it by yourself. This is just to show the level where I'm getting you and the level that I'm going to put you. So you can check by yourself if you can answer your question now, and then after we finish the lectures, I'll try to do this after every lecture, from the beginning of the lecture and the end of the lecture, and you're gonna see, did you learn something? And that's the way you can measure your own progress. So I'm sending you actually back to school. People hate school simply because in the school they don't learn properly, and they don't show. Most teachers, they do it just for money. They don't show the love to the subject, and if you don't love something, how can you make somebody else love it? You know what I mean? It's nonsense. But if you can understand the things, you'll start loving them, and you'll start understanding them, and then you'll start appreciate them, and then you're going to hurry to learn more and more things. You're going to be greedy for more and more knowledge. It's just incredible. But unfortunately in the school, because they're chasing programs, they're chasing curriculum, they're chasing many other things, they don't pay proper attention you to start loving the things. Because if you love something, you're gonna do it. If you don't love it, nobody can push you to do it. It's just with the push, it's not going to do. Better to pull, to draw into the mirror. Let me ask you the questions. First, the strongest force in nature is gravity. Yes or no? Second, all chemistry is due mostly to electromagnetic forces. Just be honest, say yes or no, or I don't know. I'm going to explain what is electromagnetic force. I'm going to explain. Don't worry. I'm just checking your level now. 3. Something can be a wave, like a radio wave, and a particle, like a pebble, at the same time, or not. What do you think? So, something can be wave or a particle, but never both. What do you think? True or false? This lecture, I named it that we can try to understand the visible by the invisible. Right? The invisible is something that we can't see, we can't just maybe straightforward hold it in our hands, but there is a way to get into that, and took hundreds of years for the humankind to get into that. So I would like to ask you to appreciate not only my efforts of making this lecture, but I'd like to appreciate the efforts of all of these people. Some of them paid with their lives, some of them is being killed, some of them sacrificed their lives for science, some of them died being exposed by radiation, like Mary Sklodowska-Curie. She's a Nobel Prize winner, but she died. She sacrificed her life for science. So I'd like you to appreciate that is given to you, all of this for free, at the convenience of your screen. Okay, I would like to start with the quotation of one very famous chemist. He's called Walter Heitler. He's a German chemist, and now you can think about how the chemistry is working and what laws, chemistry laws. And he said it very simple. He says like this: physics eats chemistry with a spoon. Physics eats chemistry with a spoon. Heitler is very important in the chemistry because he found the way to explain how the atoms actually bond, and that's very, very, very important. So all the chemistry laws can be explained in their vast majority with physics laws. This is why he says physics eats chemistry with a spoon. This is what it says. But first I would like to start going into our discussion with the discussion of some fundamental forces, and I'd like to explain what is fundamental forces. Fundamental forces are basically 4 forces, and these 4 forces are, I'm going to start from the weakest to the strongest. The weakest force is the gravity. Although we meet gravity every day, and gravity keeps me on this chair straight now as I do my lectures. But gravity is the weakest of all 4 fundamental forces. All other forces that you know, wind, solar, everything else, heat, whatever you call it, is subject to these 4 forces. This is why they are called fundamental. First is gravity. It makes the planets move. Second one is very specific force, maybe you never heard. It's called weak nuclear force, which is responsible for the beta decay. When one atom decays and goes into another atom, and then is releasing electron, and also other particles, but it's a very specific. That's a beta decay. Then the second strongest force is the electromagnetic force. And the electromagnetic force, we are familiar because we've got electricity at home. We can play with magnets, you can see it, and the electromagnetic force is the second strongest force. And actually the chemistry is based on this force. The atoms get connected to each other, the molecules get connected to each other. All the substances that we see are result mostly I say, on electromagnetic force. Obviously there is some gravity as well with some part of the chemistry, but chemistry is involved mainly in the electromagnetic force. And the first force, which is the strongest force in the universe, excuse me, is the strong nuclear force. It keeps the nucleus of the atom together. If it wasn't that force, there wouldn't be any complex atoms. Everything would be running like protons and electrons and neutrons all around. Now, I just want to tell you, if we compare the weakest with the strongest force. Now, I'm 80 kg. That's the force of the gravity. If we change the force of gravity, we change it with the strong nuclear force, I would weigh a whole galaxy. Galaxy we're talking about. You understand? That's 200 billion stars like our sun. With the planets, with the gases and everything inside. I would weigh that much. Such a strong force that holds the nucleus out. This is why nuclear bombs are so powerful, because they release the energy that's in the nucleus. You understand? Release that energy. See? So that's important to understand this for nuclear forces. So let me carry you through some chemical symbols so that you're not going to be clueless when we're talking further on about chemistry. Look, it's not so difficult as you can imagine. It's quite easy. It's just a way to represent some chemical compounds. Look at it now. There is several ways to represent a chemical compound. There is a molecular formula. That's it. There is two compounds. One is acetone, which the ladies clean their nail polish, and there is acetic acid, or in diluted form we're using it as a vinegar. And this is the molecular formula. It tells you how many atoms we've got in this molecule. We've got 3 carbon atoms, 6 hydrogen atoms, and 1 oxygen atoms. Now, the vinegar has 2 carbon atoms, 4 hydrogen atoms, and 2 oxygen atoms. Structural formula shows us much in detail how the atoms get bonded to each other. Now you can see you've got double bond, you've got single bond, you've got different functional groups like a methyl carbonyl group. Here, there we got carboxyl group, got methyl group, we've got single double bonds. It's very interesting to find out how it is. And then we've got condensed structural formula. Now the methyl, that means 3 hydrogen atoms connected to 1 carbon atom, H3C. It's represented this way and this way, and this one, it shows the double bond here. That's condensed structural formula. You can see that wherever it can be condensed, it's condensed. Then you've got ball and stick models. You've seen it. These ones, you've seen it all around. It shows the bonds and it shows how the molecule is placed in the 3D space. This is 2D, as you can see. Structural formulas and condensed formulas, they're 2Ds. ball and stick models, they're 3Ds. You can see now the methyl group. You see how it is in the space. You can see the carbonyl group also has double bonded, also represented with different colors. Black are the carbons, white are the hydrogens, and red are the oxygen. And also you can see the acetic acid or the vinegar. You can see also the carboxylic group here, how is represented, and there as well the methyl group also how is represented. And then the space filling models, you can see it's actually this is near to what it should be in a nature. This is how actually the molecule should look like in nature. Basically, I would like to tell you that for a few years ago we already have pictures of single atoms. Can you imagine? Before, when I was a student, that wasn't possible. Even some scientists thought that it's impossible, but now we can do it. There is a way to do it. The molecule, this is not the way the molecule is connected in nature. There is no sticks there. It's more like this, but the sticks and the balls are showing different kinds of bonds, and the space orientation of the molecule. That's ball and stick models. This is why it's very important. So this is the 4 ways to represent chemical formulas and chemical substances, and it's very important. So let's try to start from the very essence of chemistry. What is the atom? So let's build the atom. Atoms are built with protons, neutrons, and electrons, with the exception of hydrogen, where we've got only 1 proton and 1 neutron. Now, as you can see, the proton is positive, it's positively charged. Electromagnetic force, it's very important with the building of the atom, so it's positively charged, while the electron is negatively charged, and positive and negative makes the atom neutral. All other atoms in nature, they've got also neutrons. Right? They've got also neutrons. Hydrogen only got 1 proton and 1 electron, which is going around in a way around the proton. Okay, the nucleus of the atom consists of protons and neutrons, and there is a cloud of electrons going around the nucleus. So what is the element, what makes the element such an element with specific properties? Is it going to be a hydrogen or helium or a lithium or a sodium or oxygen? Depends on how many protons we've got in the nucleus. Now look at it. If I put 2 protons, now it's helium. If I put 3, it's lithium. 4, beryllium. 5, boron. 6, carbon. You see, it changes depend on the number of the protons. Okay. So now let's say it's helium. Now we need to put some neutrons. Why we need neutrons? Neutrons are because what's happening is that the protons, we said that they are positively charged. So they try to repel each other. Only the strong nuclear forces hold them. But the neutrons actually dilute the charge. And you can think about something like the glue to stick the nucleus together, so it's not going to disintegrate by the electromagnetic force. This is why we've got 2 neutrons in the helium and 2 protons. But now you can see it's positively charged because we've got only 1 electron, but we've got 2 protons, so 2 positive, 1 negative. We need to put another electron. Now you can see the electrons, they don't like staying close to each other. If I put it here, it moves on the opposite side. You see, and they are rotating around there. So this is how it is. Now, if we try to build, say, for example, carbon, we need to put quite a lot of neutrons, and then we need to put a lot of electrons to make it neutral. For now it is ion. Just an ion. Ion means atom which is electrically charged. That means either we've got more positive charge or we've got more negative charge. So see, in this atom we've got 4 electrons in one of the shells, then we've got 2 electrons in another shell, and then we've got total of 6 electrons, 10 negatively charged, and then we've got 6 protons, and we've got 6 neutrons. Right, this is how the atom, this is nucleus, and this is the electron cloud. The electrons are not nicely turning in such circles around. I'll show just now what they do. Okay, let me show another properties of the atom. We saw that this is an ion when you don't have a negative charge to balance the positive charge of the proton. All right, so now you can see the charge here. It says +1. If we put another proton, we've got 2 positive charges, so we've got 2 charges. That's helium. Right, so let's balance it with electrons now. All right, now you can see that everything is balanced. But now the problem now is, let's check up of the atom without neutrons is stable. Look now, it's unstable. It needs neutrons. So we put 1, it's getting stable, right? But helium is more stable with 2 protons and 2 neutrons. Okay, let's carry on. If we put another one without another neutron, you can see it's unstable. So we need to stabilize it with now, but we've got net charge is positive because we've got 3 protons, but we don't have 3 electrons. We need to give him another electron. Now, as I said to you, this is not a nicely figured circles like you know, all of these circles. It's a cloud. This is what it is. It's a cloud. So we don't know where is the electron. The electron is a wave, so it's like a cloud. But you know, for simplicity, we sometimes illustrate the atom like this. Now I want to show you another thing which is called mass number. Mass number is the total number of the protons and the neutrons. It's 6. 3 protons and 3 neutrons. See? So this is how it is now. If we carry on, then we're gonna go beryllium, boron, carbon. Now we need to put, it's unstable. You see? We need to put more neutrons. Now it's stable. See, you've got 6 neutrons, the mass number is 12. Otherwise, it's not stable. See, mass number is 11. But now you see the charge. Whoa, it's +3 because we need to put -3 to make it neutral. So we're putting 3. Right, and as I said to you, it's a cloud. It's not a orbit. Right. Now, to give you a very familiar figure of how to understand the atom, how can we compare actually the atom? Now, if the whole atom with the electron cloud can be compared to a stadium, the whole stadium, with the walls, with everything, then the nucleus is just the ball at the center of the field. Now can you imagine, the whole stadium is the whole atom with the electron cloud, the electron is moving around, but the nucleus is just at the center, and is just if we can compare the atom to a stadium, the nucleus is going to be as big as ball, just the ball. But the nucleus carries all the mass of the atom. The electron is just the 1/2000 times of the weight of the proton, right? So it's negligible mass, not even 1%, the electron. So almost all the mass is concentrated into the nucleus, but you can see the atom is quite empty. Now you can ask a question: if it's so empty, why we feel solid objects like this table, wall, glass, and things like this? Why we've got solid objects if it's so empty? The problem is, as I said to you, chemistry is grounded on the electromagnetic force. One molecule is connected to the next one with the electromagnetic force so strong that you can't go through it, right? Although it's empty, but this is very miniature space, so the molecules get together, they get also connected, so you can't get through. The atoms also get together, very strong. You remember I told you the strongest force in the universe is the strong nuclear force. So that's the way we to think about the atom. This is the magnitude of the atom. Now you may start thinking about, okay, now who actually told us that this is the truth? You know, there is some people that hate science, and they said science is all lies, just to manipulate the people and talk all kind of rubbish, belief in the flat earth and all kind of stupid things, and they hate science. First, they don't understand it, and second, because they don't understand it, they hate it. So now they say, who told you that? Look, now the experiments that has been done to discover the atom, you can do it yourself. It will take you just a little bit some machinery and some things at home, but you can do it actually if you'd like to do it. And first, there is a few things that get discovered until we get into the atom. What you see here is one of the brightest chemists, Antoine Lavoisier. It's a French guy with his wife. They both do science, and Lavoisier tried to figure out some experiments with different compounds, tried to figure out if the matter, actually the whole matter, is preserved when it goes to transformation. So first he measured the mass of the weight of the water. Then he made it boil, turned it to a steam, and he measured the weight of the steam, and he found that the steam has the same weight as the liquid. And then he turned the steam back to liquid water, the vapor turns it back to a liquid water, and found that the weight is the same. The mass is the same, that means. It's very interesting that the mass is preserved, although we've got two different physical states, two different phases, as it says. One is the liquid phase, the other one is the vapor phase. Then he did another experiment. He took a candle, you can do that by yourself, and he took quite a big jar. If you take a small jar, the candle, when you put it burning, is going to burn very quickly and it's going to go. But he put quite a big jar, and he noticed that while the candle is burning and is reducing the wax, the weight stays the same. That means the compounds which the candle with the flame converts into a gas, that means carbon dioxide and water vapor, that have the same weight as the wax. And that's very interesting. So he found the way of establishing the law of preservation of mass. Then he did another experiment. He took iron, hot iron, and poured it with steam, with hot steam, and he showed that the water is converted, right? The steam reacts with the iron, with the hot iron, turns it into a rust, and it produces hydrogen gas. All right, but now the weight of the steam and the iron is exactly the same as the weight of the hydrogen and the rust. That means although we're changing chemical compounds by reaction, you can see the mass is preserved from the reactants to the products. So that the reactant mass is the same as the product mass. And this is why he established the law of preservation of mass. The mass is preserved. If the mass is preserved, that means there is something very fundamental with these particles that stays the same. And that's very interesting. Then came another chemist, Joseph Proust, and he tried to experiment with different metals and their compounds together with oxygen. And then he found that every single mass unit of the metal is getting with the definite proportion, with a complete definite proportion with the oxygen. And then it makes the metal oxide. Metal and oxygen, metal oxide it makes. Metal oxide, you're familiar. Rust. Iron and oxygen makes rust. We're going to study how it's done. You're familiar with metal oxide. Also, he found that if you combine some metal with the oxygen, they are combined with very, very definite proportions. So this is, he invented the law of definite proportions. So let me explain you what's the law of definite proportion with specific molecule. Now we've got a 1 gram of carbon dioxide. Now by mass, they are 72.7% oxygen and 27.3% carbon, or 0.273. We're putting it 1 gram so that it can be convenient, so that you can see it. The percentage is there. Now, if we take 16 grams now, not 1 gram, you can see that the proportion is exactly the same. 11.64 grams and 4.364 grams, which is exactly the same as a proportion of 72.7% oxygen and 27.3% carbon. Now, if we take another compound now, that was the thing that the opponents of Proust actually argued with him, is if you take another compound, carbon monoxide, then you've got a different proportions. You see, now you've got 57.1% oxygen and 42.9% carbon by mass. Now, this is actually the law of different proportions. Now you can see it is very clear that whatever mass you take, whatever source you take of the compound, is going to be water from reaction, or is going to be water from different places, or you've got different quantities of the compound, in this case carbon dioxide, the composition is exactly the same with proportions. So that's a very important thing to understand. This is the excellent example on the law of the definite proportions. Similar law, the law of constant composition, states that the compound stays the same, doesn't matter where you get it from. If you get the water from the ice or from the steam, did you get the water from Antarctica, or you get it from China, or wherever you get, if the compound is pure, doesn't matter where you get it from different compounds or from different reactions, the compound has the same elemental composition by mass. It's exactly the same. So that's another law, the constant composition. For example, the compound that we study, water, it's exactly the same by mass. It's 11.2% hydrogen and 88.8% oxygen. Wherever we get it, it's always the same if it's pure. If we get it by different reactions, say for example, if we've got caustic soda and you've got hydrochloric acid, and you mix it together, and we're gonna get table salt, sodium chloride, and water. This water that we're gonna get in the result of this reaction has the same proportions by mass. 11.2% hydrogen by mass and oxygen 88.8%. That means that's a law of constant composition. Together with the law of definite proportion and together with the law of preservation of mass, now we start getting very near to discovering the atom, but not so near. We need something else. Now, when Proust published his law, actually he was ridiculed. People tell him, you don't know what you're talking about. Some leading chemists like Louis Berthollet says that the compounds actually can be connected in any kind of proportion, not such a thing as a definite proportions. And scientists refused to recognize it at this time his discovery. Now, their own experiments shows that they showed that the samples of compound of tin, right, formed with oxygen, the content of tin varied. It shows that, and that's clear experiment. But those scientists did not realize that their samples were actually mixtures of two compounds with different components, different oxides of the tin, not the same. You know, one is with one proportion of oxygen, the other one is with more oxygen. They're different compounds. You see, they are not the same compound, which Proust was able to demonstrate, and the time passed and his theory started getting little bit accepted. Well, all of this controversy, French controversy, was raging. In England, there's another scientist, John Dalton. From there comes Daltonism, or a color blindness. He tried to make research on color blindness, and this is why it's called by his name, although he didn't find quite the reason for color blindness. His research is fundamental. He started this is why it's called on his name. He was a very humble man. All his life was science, science, science. And he discovered that when two elements combine to form multiple compounds, the different masses of one element that combined with a fixed mass with the other element will be in a ratio of small numbers. And it can be 2 to 1, like a hydrogen to water, to oxygen in water. Can be peroxide, 2 hydrogens to 2 oxygens, but you can see always is a small number and the whole number, not half oxygen. You see. Now, Dalton proposed scientific theory that explained the Proust's theory of Proust's actual law of definite proportions. He observed when two elements react to form different gaseous compounds, they may form 2 or more compounds with different compositions. In this way, he confirmed the experiments which Proust did with the tin oxide and tin dioxide. So Dalton experiment not with tin, Dalton experiment with gaseous compounds, and he found with the gaseous compounds that they agree with the findings which the Proust confirmed with his law with definite proportions with the solid compounds. He did it with metal oxides. Now he did it with gases. Now, Dalton. Now, if we look at the notes of Proust, Proust discovered that tin and oxygen form one compound which have 78.8% of tin and 21.2% oxygen. And then you've got another compound of tin with the oxygen, which have different proportions, which are 88.1 and 11.9 oxygen, 88.1 tin and 11.9 oxygen. And now Dalton start calculating the ratio between 88.1 and 11.9 and the other ratio 78.8 and 21.2, and he realized that actually they are twice that of the first compound. So the first compound has more oxygen, but the ratio is twice as much as the second compound. And now he tried other compounds and he found that we've got the similar results, that compounds when they are paired with other when the one element is paired with another element with different compounds makes different ratios but with whole numbers, like in this case it was 2 to 1. So now sometimes they differ by a factor of 2, as with oxygen and tin. Sometimes their compositions vary by different factors, by 3 or by 4. But it shows that the compositions always differed by ratios. We're talking ratios here of small whole numbers. And this pattern, when in science we see a pattern, now we try to make a hypothesis, and this hypothesis leads to establishing a theory, and the theory gets established to a law. And when you try to prove it all around in experiment, it's found that yes, there is a law, and this is called the law. He formulated the law of multiple proportions, and this law of multiple proportions says that when two elements combine to make two or more compounds, the ratio of the masses of one of the elements that combine with the given mass of the second element is always a ratio of small whole numbers. Another example will give you. When 15 grams of oxygen combines with 10 grams of sulfur, okay, under one set of reactions conditions, it forms and it makes this compound, sulfur trioxide. Then we've got another set of conditions where we've got 10 grams of oxygen combines with 10 grams of sulfur and have a different compound. But look at it now, because the first time we had 15 grams of oxygen combined with 10 grams of sulfur. The second time we've got 10 grams of oxygen combining with 10 grams of sulfur. Look at it, the ratio, 15 to 10, which is 3 by 2. You see, 3 divided by 2. 15 has 3/5. 3 by 5 is 15. And 10 gets 2/5. So 10 has 2 by 5. And now, this is actually a small numbers, a whole small numbers, and the ratio is 3 by 2. You see, now I've got 3 in one compound and 2 in the second compound. Now that's the law of multiple proportions. To explain this law, he actually proposed this theory, and then after it turned to a law. Thus, the ratio of that we just saw, of Proust's tin oxide, it's 1.39, contains 1 atom of oxygen, and the other compound that he did contains a ratio of 0.269, which is actually 1 to 2. 0.135, if you multiply it by 2, it makes 0.269. It's very close to. These atomic ratios actually now are reflected in the chemical formulas of the compound SNO and SNO2. So now in this way now Dalton realized that actually we've got a small particles that always combine in a different proportions, multiple proportions also, specific multiple proportions, the whole number proportions, whole small number, and in this way he actually proposed his atomic theory. So one element can combine with the fixed mass with other element will be always, their masses will be a ratio with a small numbers. And then a bright idea came to him. Look, the atom theory, atom is a Greek word, means atomos, that means it cannot be divided. That idea came also to the Greeks, particularly Demosthenes, but they didn't have the facilities and the labs which Dalton, Lavoisier and Proust and others have to discover this. They don't have precise equipment to do that. They just, the Greeks and particularly Demosthenes, consider it as a philosophical concept. That means Demosthenes said when you cut something in small pieces, you're gonna come to such a small piece that you can't cut anymore. And that small piece is called atom, where you cannot, that actually makes the different compounds around us. But that's more as a philosophical concept, not as a chemical scientific concept. First, Dalton start establishing the concept of the atom as something that is the fundamental unit of all compounds around us. And you know, his only fun, his only pleasure was Thursday afternoon. He used to play balls. You know, it's called lawn bowling. You've seen some old people used to play this all lawn bowling on Thursday afternoon. And he realized that the atoms are actually small balls that get together in a definite proportions, in a multiple proportions of the whole numbers, just like the balls. They get together. Funny enough, he said that the atoms get bonded together with the hooks, get stuck. That's not true. Atoms are not get connected to the hooks, but that's almost 200 years ago. Can you imagine? But he discovered the concept of the atom. So now what is happening at this stage? Now we've got the fundamental laws which can make us discover the atom. So let's revise them. First, the law of conservation of mass. If we've got a methane, it's a gas that we're burning, combining with oxygen, because without oxygen there is no burning. If we combine one molecule of methane with 2 molecules of oxygen, we're going to have 1 molecule of carbon dioxide and 2 molecules of water. Now if you count the atoms before and after, you're going to see that they are the same. And it's all about the law of conservation of mass. We've got 4 atoms of hydrogen. There is it, 1, 2, 3, 4. In the products, that's a reactants, that's a products. You've got 4 atoms of oxygen. Again, 1, 2, 3, 4. So the products are 4 and the reactants are also 4. It's a reactants and it's a product. And then you've got 1 atom of carbons in the reactants and 1 atom of carbon in the products. That's the law of conservation of mass. Then comes Proust, and there he says that there is a law of definite proportions. So now this law states that the material, the same compound, we're going to have the same definite proportions wherever it is. Is it a kilogram? Is it a 10 tons? Is it a whatever it is? If it's the same compound, you're going to have the same definite proportions of the atoms. And there is an example with water we're going to give you. 1 molecule of water and 5 molecules of water. In 1 molecule of water, we've got 2 hydrogen atoms and 1 oxygen atom. Now, the mass unit of hydrogen is 1 because we got only 1 proton. The mass unit of oxygen is 16 because you got 8 protons and 8 neutrons. So now, because we've got 2 hydrogen atoms, we've got 2 mass units of hydrogen and 16 mass units of oxygen because we've got only 1 oxygen. Now I've got 5 molecules. That means we're going to have 10 hydrogen atoms, and then we're going to have 5 oxygen atoms. And because their mass units are, one is 1 and the other one is 16 per atom, then we're going to have, because we've got 10 atoms, we're going to get 10 mass units. Oxygen, we've got 16 mass unit per atom. We've got how many atoms? 5 by 16, 18. 80. This is how the law of definite proportions. And the same scientist Joseph Proust also formulated the law of constant proportions. That means this proportion is going to be constant wherever it is. Is it ice? Is it a vapor? Is it water? Whatever it is, whatever quantity, wherever the source, wherever it is, if it's a pure water, it's going to be exactly the same constant proportion. Definite proportion and a constant proportion. And then comes Dalton, and when he studied Proust's experiments, he says, okay, now we've got not only definite proportions, but they're multiples of small numbers. How does it do that? Now we're going to give you an example like I did before with sulfur trioxide and sulfur dioxide. Sulfur trioxide, there is a 15 grams of oxygen that combine with 10 grams of sulfur to produce sulfur trioxide. Sulfur dioxide, you've got 10 grams of oxygen combining with 10 grams of sulfur. Now, in one, you've got 3 atoms of oxygen in the sulfur trioxide, and the other one, you've got 2 atoms of oxygen. Both compounds are compounds of sulfur with oxygen, but in different conditions made. In one, it's made in a different condition with less oxygen. Now I've got sulfur dioxide with 2 oxygen atoms, to 1 sulfur. In the other one, we've got 3 oxygen atoms to 1. But now you see, it's multiple proportions. Now we've got 15 grams oxygen compared to 10 grams of oxygen. And in the one we've got 3, in the other one we've got 2. So 10 divided by 2 is 5, 15 divided by 3 is also 5. So the single unit, the atom, has 5 grams into this molecule where it gets compounded. Obviously there is a billions and billions of atoms, but in the formula of this we've got one atom of sulfur and 2 or 3 atoms of oxygen. So one of the oxygen contributes 5 grams to the weight of the oxygen in the molecule, the 3 atoms of oxygen. So we've got multiple proportions, and this one are the proportions are 2 to 3, 3 to 2. You see, it's all integers, it's not fractions, it's all integers. That means something that we can't divide, atomos, not divisible. This is why we've got how the atom got discovered. It will take another 100 years. The stormy 19th century, where a lot of discoveries are done. Bear in mind, the electron is not yet discovered when Dalton formulated his theory of the atom. Not the proton, not the neutron. Nobody knew about these things. It have to take another 100 years to be discovered. First the electron, then the proton, and then the neutron. So now, when these discoveries are made, then we've got a different approach now to the atom. And now all the scientists now try to construct the whole model of atom, how the atom and how the electrons are moving around. And they start inventing their theories. So there comes a brilliant scientist, Niels Bohr, who invented his model of atom. He's a professional goalkeeper, excellent player, used to also love his motorbike. You can see him here with his wife on a motorbike. And then when he discovered the model of the atom, where the nucleus in the center and the electrons are turning around with specific orbits, like we saw it in the representation before, when he constructed the atom, he won the Nobel Prize. And Carlsberg beer factory in Copenhagen in Denmark gave him lifetime supply of beer. Actually, they made a pipe from the factory to his house, so he could wash his dishes and take a bath with beer if he wanted. He got a lifetime supply with beer. This is how the Carlsberg beer factory actually rewarded him for his discovery. But let's look at this model of the atom. The atom consists of, say, the simplest atom, hydrogen atom, consists of one proton and one electron that turns around in a specific orbit, in a specific distance from the nucleus. You've got different levels. You've got level 1, level 2, level 3, level 4, level 5, and level 6. And these levels are different energy levels. So if we bombard these things with light, it goes to a different level, and then when it comes back to the normal first level, because it releases light, it releases a photon. Look at it now. Different colored photons depending on where the electron was pushed by this energy, by the light. You can see red photon is pushed. Now this one is again a red photon. See, again a red photon. When it returns back, it pushes to a different level and releases red light, red photons. Now it returns back and is pushed. You see, when it returns back, it releases the energy. Now it's blue. You can see again blue. It's pushed. Now red. So specific orbits depending on a different level of the energy between the different energy of the light that strikes him. See, so that's very, very important way to understand, and that's how it is. That's the Bohr model of the atom. Now, there comes another brilliant French guy. It's called de Broglie. He says, no, this is not true. The electron is not turning around in specific orbits. Otherwise, there is no way to explain how the electrons are bonding. The basic of chemistry is bonding of electrons. They make the electron clouds make a new electron combination where it's a new cloud now with the two or more electrons, and now we've got a different compound. So it's not these shells that are there in these orbits cannot explain this phenomenon, how the atoms get combined into a new compounds, because it's not able to explain it in this way. Can't explain the bonding. So de Broglie says no, the electrons are not particle with specific orbit, they're wave. They're waves. And that is incredible theory. And he really proved that the electrons are wave. Just the light has a dual nature. It is a particle and you've got also a wave nature, but also the electron got also a wave nature, as you can see. Yeah, that's how it is. Now, if we turn it 3D, you can see the wave. And because there is no way you can know where is the wave, where is the electron around the wave, there is a total uncertainty where is the wave. So that is where de Broglie came with his model of atom, and that was absolutely true. And as you can see, the wave, let's go back here. It's can be 3, can be 5, can be different wavelengths, but always an integer, so that it can make the circle. Otherwise, you won't make the circle, the full circle, full cloud around the nucleus. Then comes a Schrödinger, a brilliant German scientist. So now we need to see it now. His model of atom. He says yes, the atom and the electrons around it are waves, but they are not in a specific place, just like a Bohr did it. But also we can't find them in a specific exact place. So they're like a cloud. You see, look at it. This is the cloud. This is the cloud. Where is it? When the photon, when the light strikes the electron, it goes to the, now I'm exciting the electron, it goes to the different level. But you can see where is the brightest light, there is the most probability the electron will be there. There now I see. I'm putting light deliberately so that we can excite the electron, we can see the cloud. Otherwise we won't be able to see it. If I stop the light, won't be able to see the light. We're going to see only the orbit of the electron around, but as you can see, it's a cloud and is a wave. See, it's a cloud and is a wave. So I need to put light so that to excite, so you can go in the different orbitals. But again, bear in mind, this is a cloud, this is not a specific orbit. Orbital and orbits are two different things. So this is how the atom is done. Now comes another brilliant physicist, Werner Heisenberg, and he says, yes, the electrons are in the cloud around there, and there is a probability we can find them in the where the cloud is in this schematic presentation, the brightest. But now there is no way we can know the speed of the electron and his position at the same moment. You can know one of them but not both of them together, because as soon as you know the speed of the wave, you won't know where is the place. As soon as you know where is the place, you won't know the speed. And there is one cop that stopped Heisenberg, and the cop asked him, do you know what's the speed you're driving? And Heisenberg says, no, I don't know the speed, but I know where I am. So that's it always. If you know the speed, you won't know where you are, and if you know where you are, you won't know the speed. And that's the law of Heisenberg. It's called the law of uncertainty. You can know one, and you can know the other, but not two of them together. So that's the concept of the developing of the atom. So I think it's a convenient time to close our lecture at this time, and to continue our search for the properties of water and the chemistry in the next lecture. But first, let me try to explain you the 3 questions that I asked in the beginning. The strongest force in the nature is gravity. True or false? You know very well it's false. It's a strong nuclear force. Second question, all chemistry is due mostly to electromagnetic force. True. And something can be a wave or a particle, never both. Yes, it can be a particle and a wave at the same time, just like an electron. So thank you very much for your attention. I'll see you next time.